The next event we have on our schedule is bridge building. And the purpose of this event is to build the lightest possible bridge that has the highest possible structural efficiency. So, sorry, let's rephrase that. It's to build the lightest possible bridge that can hold the most weight while meeting some certain specifications. And the specifications are basically you have to span 45 centimeters. So there's basically a gap 45 centimeters in length that you're allowed to place the two ends of your bridge on. Now, what is this structural efficiency? This term essentially defines the score that you'll get in this event. It is the ratio of the maximum load that your bridge can hold to the weight of the bridge itself. So for example, a bridge that weighs 15 grams and can hold up 15 kilograms will have a structural efficiency score of about 1,000, because 15 kilograms divided by 15 grams is 1,000. Now, that's the score you'll need to win at regionals, or I think that's what it was in the years I did it. So when you get to states and nationals, the structural efficiency goes up another order, another kind of a bit. So it's really difficult. So think about it, a 2,000 or 3,000 score, which I've heard some teams did in several years past. That means they held up all 15 kilograms with a weight of 5 grams. And that's very difficult because consider, this is actually balsa wood. It's the lightest possible wood that, is known to mankind, and it's really easy to snap. So think about holding, I guess, the weight of your backpack with a bridge built out of twigs and tiny, very thin twigs at top. So it's really challenging. And I guess you can see the challenge and a bit more in this YouTube video by the official Science Olympiad channel. So let's watch it.
Oh, so the loading piece pulled right through and maybe it hit the side as it was falling.
Pull the handle back, you go as fast or as slow as you like. Once you start, you can't stop.
Experiment with as many different things as possible until you get your best design. You go, you test it, and it's broken. Now you don't have a new one to do, but you know what the design then.
I'm better
High as you can. Probably good right there. Hook her in the rim and make it exciting. Hey! Good work.
Well, that was that. You saw a lot of bridges fail. And that's kind of the point of this event. You build a bridge and you test it until failure. Now, you might think, okay, this is kind of easy. You grab some glue, grab some sticks of balsa wood, and you do some stuff. You glue them together, and voila, get a bridge. You'd think it's that easy. It's not, because the first bridge that you'll build will hold a disappointingly low weight. And in fact, you will be surprised at how little it could hold. So you can't just rely on gluing stuff together unsystematically, because you'll get mediocre results and you'll have inconsistent performance. So to be successful at this event, you'll need lots of trial and errors to bring your bridge to a level, to improve your bridge with each iteration and bring it to the state of perfection, which is a bridge that is reproducible and has high structural efficiency. And teams go through dozens of these designs over a season. In fact, maybe 100 designs is probably what we should ask for. So there are so many small things you could change here, like the number of trusses, their angles, the glue you use, the wood you use, and each one of them has a very big impact on the performance of this device. I'm sorry, I need to like exit a little bit to modify a slide, sorry. There we go. I had a thing I forgot to delete from previously. So yes, so that's kind of the things you need to do to be successful at this event. And you think, oh my God, why is this so complicated? You need to do trial and error. You need to come up with designs and stuff. Well, it is quite important. And look no further than your bridges in real life. You drive on these all the time when you go on a freeway, when you go to San Francisco, and yeah, you really want to trust the bridge that you're driving on. You don't want it to fall, right? And building bridges is not that easy. I mean, take a look, concrete, and it's a bridge. Concrete is heavy. How do they make this thing? Yes, we can trust a bridge. Well, concrete works a bit differently than metal trusses, and if you'd like, you could come to our workshop and I'll teach you why. But concrete is heavy, and you need to support that weight somehow. Or look at this bridge, has such a huge span. How do you hold this weight up without propping it up in the middle and without it sagging? So the area of structural engineering, civil engineering, deals with designing these structures. And they're not limited to bridges. Like this construction crane is also supporting a very long weight. Like, I don't know, they're lifting up a heavy block of steel up to a tall floor. They need to make sure that you can bring this block of steel all the way up into the corner. And that's going to be a really, really heavy load for the crane. Now, I mean, to nail this point even further, why this type of discipline, this area of engineering, this event for Science Olympiad is important, let's just look at some bridge failures. So this is the Firth of Forth Bridge. It was built in Scotland over a century ago. What happened here is it looks like part of the platform was torn out because of the wind. Yeah, the wind blew hard and it collapsed. And I guess if you don't think that wind is a big enough issue, well, let's watch this video of the Tacoma Narrows Bridge. You'll be convinced otherwise quite soon.
Dawn of a fatal day, and the wind begins to speak with a roar that no man can fail to hear. In a 40-mile-an-hour gale, the center span weaves like a ribbon in a swinging twist that you wouldn't believe possible unless you could see it as you do now. There's an automobile caught on the heaving roadway. The 11,000-ton center span twists and strains the giant cables that support it. Cables of 6,300 wire strands, each 17 inches thick.
What's happening here is it's a bridge, but the wind is so strong that it's swinging and it's like doing these wavy patterns. Like, holy, that's so that bridge is going to fall. Well, we will skip ahead right to the part where it crashes. Let's see. Let's go here, I think. Yeah. So there was a guy on the bridge and he decided to leave. Best not risk his life. And I guess we can watch the final dramatic moment of how this bridge collapses.
No structure of steel and concrete can stand such a strain. Steel girders buckle and giant cables snap like puny threads. There it goes! Engineers are divided as to the cause of the disaster. Some claim it was the use of solid girders.
Yeah. Engineers later figured out the cause of this problem. It was basically the fact that the wind was blowing. It has to do with resonance frequencies and the Struhal number, which comes from aerodynamics. So the wind was blowing in such a way that it matched the resonant frequency of the bridge. And just like you have swings, if you push the swings at just the right moment, they will swing very high. Something similar happened to the bridge, and eventually it couldn't hold anymore and crashed. So I guess let's hope that the bridges you build won't crash as spectacularly as this one, and they'll hold the rate that you designed them to.